Cool. All right. Uh, Welcome to the ML Performance Reading Group. Today we have a presenter talking about LMCache. So I'll hand it over to you.
Yeah, hi guys. My name is Arshad. So I'm interested in building a Rust-based kind of VLLM alternative. So investigating quite a lot of these kind of techniques that are used to make efficient inference services. And one of the key ones is a KV cache. And LM cache is kind of like the preferred one for bigger installations. So if you've got more of like an enterprise scale infra system that you need to build, LMCache is one of the top ones. It's an open source project. It's written in Python, but the performance is really excellent. So I'll give a brief outline of the my presentation. So yeah, I've kind of condensed the paper into this. So first of all, the motivation for why we need a KV cache. Then I'll be giving just a brief intro to what is KV caching, and then a couple of key techniques that we need to be able to implement or to that LM-Cache can relies on. One is PD disaggregation, which is Prefill-decode disaggregation, and the other is page detention. The whole architecture of LM-Cache kind of needs that. Then we're going to look at LM-Cache, its philosophy, uh, and kind of like what drives the overall design of LM-Cache. Then we're going to go through the architecture, kind of an overview, and then really to kind of take a request from the top, hitting the inference engine through the various layers and how LM-Cache kind of like feeds into that. Finally, the LM-Cache API, which is one of the ways that it can be plugged into any inference engine, so things like VLLM or SGLang. Finally, I'll give a little bit of an evaluation of the system compared to the built-in cache systems in things like VLLM and SGLang, and a couple of commercial products. The paper doesn't mention the exact companies, and because they're black boxes, probably the companies may say it's not quite a fair comparison, or maybe the way it was done, but it gives some numbers as to the comparison of LM Cache against some commercial alternatives. And then finally, a couple of resources if anybody wants to kind of know a little bit more about LM Cache. So what's the motivation? So really, because we're looking at enterprise class kind of like inference systems that we want to build, essentially these are going to be lots of users, uh, uh, quite often perhaps using documents in their chat sessions. It's going to be multi-turn, going to be quite complex use cases that they're going to need, and it could be potentially thousands of users. And quite often requiring thinking traces. They may even be using agents, which would need quite large context because they over quite a complex process that the agent is going through. Uh, so, and one of the reasons that Atom Cache exists is really that the its efficient utilization of the infra that you have in terms of what the GPUs you have, what the compute instances that you have. So LM Cache allows you to kind of get an idea of, okay, uh, certain things are using the GPU more, certain things are using the GPU less, and how do we break those kind of down and to make the whole process kind of more efficient. Okay. So why KV cache in the first place? So what do we need it for? So if we look at so modern LLMs are decoder based only as transformers. And what that kind of means is that you give it a request, potentially a very large request, and then that goes into a set of transformer layers, and generates a next prediction token, and then that is auto-regressively generating additional tokens until finally the whole request is completed. So it's that kind of a workload. And the way we normally do this is that right at the bottom of this diagram, we've got the input, which then goes into which is then converted into input embeddings. Then it may go into an RMS norm, and then we've got these three vectors that we multiply the input, this past input we have. And the three vectors are Q, K, and V. That these are the query key and value vectors that we generate. Now, that is generated by a fairly large matrix multiplication. So three different matrices: the Q weight matrix, the K weight matrix, and the V weight matrix. And that's quite a GPU heavy task. And then that generates quite a lot of data, which is these QKV. And so if you imagine that you've got quite a large request, which has come through, and then perhaps the users entered another query which uses the same request. If you're going to have to compute the Q, K, and V again, then that's a computation you just did a moment ago, but then you have to do it all over again. And this is the way really the first initial version of inference engines used to work. And essentially, the reason why we use the KV cache is to avoid that kind of redundant computation. Because we already did the the KV calculations before, we don't want to do them again because they're really exactly the same. So that's kind of like why we have a KV cache, is to save that redundant computation. And this is like a little bit of like a more detailed kind of like view of exactly where the KV cache is kind of like coming in. So on the left, we've got kind of like a request that came in machine learning is, and then that went through the network. And in the first iteration, it was multiplied by the WK, WQ, and WV. These are the three KQ and V vectors, which generates the query's keys and values, and then potentially generates the fun as the output. But the next token that we need, we would essentially have to redo that with one additional token down at the bottom. And this is where the saving is going to come from, because potentially we've got the same tokens here, or the calculations which we already did, and the same calculations here. And really, it's only one additional sort of row that we have now for the, oops, sorry. So we have just one additional basically row in this guy, which is going to be used. And so we don't want to have to do all of that. So that's basically why KV caching is. If we already have done that, why do it again? We can just load that from a cache. Now, one of the other things that LMCache, because of the way it's architected, is that it's kind of assumed that you've got a prefill-decode disaggregation in your system. And essentially, this is pretty much the previous bit, which is the prefill is your original request, which you've converted to these keys and values, which are being stored. Now, the issue here is that when you've got a request that's come into the system, you're having to do this massive amount of computation, which is this whole batch of tokens that have come in as a request, and you're computing the keys and values which are going through the network. So this is a very GPU heavy workload. Now, once you go into the decode phase, now you're doing it a token at a time. So the amount of GPU compute you need now is a lot less, because you're only essentially doing one additional kind of row down at the bottom of the next token, which is then going to be auto-regressively gone through the network to generate the next token. And because of this, you don't really want to waste a really expensive GPU doing both of these tasks. So depending on your workload, if it has got a large request that has come in, then really it's better if you split this up, so that the compute heavy bit, which is the prefill, is done on an expensive fast GPU, potentially running on a different instance. And then once that's done, it goes through a separate decode instance GPU, which might be a cheaper one, because here there is compute, but then there's communication as well, because you're having to take that token that's just now being generated, stream it back to the user while you're then going to start generating the next token. So because of this kind of like mismatch, the way LMCache is built is that you can disaggregate these two, because the caching layer is completely separate from the GPU. It's held in like a different system. You can have the prefill generating the cache and storing it, and then the decode making use of that cache as it does the decoding. So I hope that kind of makes sense as to why you want this prefill decode kind of breakup, because the two workloads are different and they don't need the same kind of compute to do them.
Can I ask a quick question?
Yeah, sure.
You mentioned that for the decoding phase, it can perhaps be done on a cheaper GPU. I understand why it's not like a flops bound workload, and so you don't need like the heavy tensor cores and whatnot from like say, whatever B200s. But you still, it's like a memory bandwidth bound operation, right? You're like moving the KV cache from global memory into like on-chip memory to do the actual like dot products and compute the scores and whatnot. So don't you still want? I mean, I don't really work on inference, so I'm just curious why. Like, wouldn't a cheaper GPU have lower memory bandwidth capacity, and so you would still be like bottlenecking yourself a bit? Wouldn't you want something with like very high memory bandwidth capacity?
Yeah, it kind of depends on like how much of the KV cache needs to be in the GPU. So like all of this is kind of dependent on like your workload. So if the KV cache was really massive, then you would obviously need a bigger GPU with kind of like more kind of memory in it.
Hmm.
Uh, but there is this trade-off now where if you're saying, okay, I can fit a certain level because of the way, obviously that you do need to have the KV cache, but you don't need the full kind of size of the matrices in there. So potentially you could have a cheaper GPU, and I think uh, I've seen some examples on the internet where people are using I think L40 GPUs on the decoders, whereas you're using the higher end
Hmm.
GPUs on the prefill. So
Hmm.
it is kind of like a potential trade-off that you have, but it all depends on your particular kind of like use. But it's a fair question. Uh, um, uh, yeah, yeah.
Okay.
Okay. So and the next kind of something that LMCache kind of requires is page detention. So LMCache is kind of very heavily into pages and batching kind of requests. Uh, so basically, one of their sort of like uh, one of not necessarily insight, but obviously we know that every device, when we're reading from it or writing to it, has got like a certain bandwidth, and depending on how much data you're batching into it, you will get a certain throughput from it. What I mean by that is that if the amount of data you're sending to and from that device is kind of like really small, let's say you're sending it a byte at a time, then just the overhead of creating the connection and actually sending that one byte across and then sort of closing the connection, so that's going to be incredibly inefficient. So virtually every device has got like a sweet spot of a certain size of page of amount of data you can send to it, which is the most efficient way of transmit data between you and that device. So the GPU may have a certain chunk size that it prefers. Obviously, having too big a chunk might mean that it's broken down within its kind of like SDK. So you want to avoid that. Um, uh, and so basically, LMCache really prefers to work in pages of data. It doesn't work on individual tokens. It works on a page's worth of tokens. And that page is not massive. It can be like 16 tokens or 20 tokens, but it's not like a single token at a time. And the reason it does this is that it would like to kind of like virtualize the memory inside the GPU. So let's say that you've got quite a large request. It doesn't want to really create a buffer in the GPU for the whole of that request. Because what it's trying to do is, let's say you've got 5 requests, but they're all different sizes. So if you're allocating the whole buffer inside the GPU for the different requests, it means you've got different size buffers in the GPU, which depending on how they're used can lead to kind of like inefficiency. So you may have kind of like gaps in the memory, so you get like fragmentation of the memory as you're using it. So what they try and do is they actually treat the memory inside the GPU in kind of like in a virtual way as a set of pages. And it's pages you allocate, pages you deallocate, and so which means that it can make more efficient use of the memory. This also allows you to then potentially reuse pages. So for instance, if you've got a system prompt, which a lot of requests are going to use, then the pages that are needed for that system prompt can actually be shared amongst the different the different computations. Um, and this is how page attention works. So page attention doesn't actually work on a whole kind of like a flat tensor. It breaks it down to pages, and your query also is then like a list of pages into sort of global memory. And the page attention kernels are aware of the fact that there's this indirection, and they use that. And there's a couple of reasons why LMCache wants to do this. One is because, as I said before, because it would prefer to send a whole load of pages to whatever devices. Let's say it's moving data between CPU memory and GPU memory. Well, it doesn't want to do it in small little chunks. It would prefer to send a group of pages across because that's the most efficient way of getting data from the CPU to the GPU, say for instance. So LMCache really relies on a page attention inference engine because of the way its KV caches are implemented, because they're all page based. That's a requirement of the system. So from these two, the two main requirements that we have from LMCache are it has to be page attention and it has to be Prefill-decode. Those are like the two main requirements that we need from your inference engine to be able to use it. So this is kind of like a summary of why you can go for page attention. So memory allocation traditional is you get contiguous blocks and a pair sequence, and that means you get potential fragmentation. Under page attention, you get fixed size pages. Management is on a pair sequence, whereas page attention, you get a global pool of pages from which you can request pages to use for whatever memory needs you have for a query. And flexibility, on the one hand, you have rigid and you get potential wastage because all the different queries are all different sizes, whereas page attention, you get dynamic mapping because a query is essentially a group, has pointers to the pages that make up the query. So that's this dynamic mapping we're talking about. And what this does allow is page sharing, so that if a page, so it's like a system prompt, because the prefix is exactly the same amongst the different queries, potentially you may already have that available. So you can just reuse that page without having to do that. So that's kind of like the difference, and LMCache kind of makes use of that. Okay, carrying on. I don't know if anybody had any questions so far. I'm going pretty quick. Okay, carrying on. So this is kind of like the philosophy of LMCache, what kind of the overall kind of approach they have for what they're implementing. So first of all, they want to treat the KV cache as a first-class citizen. The first kind of inference engines, they did use a KV cache, but it would be within a particular GPU within the machine. So that it was ephemeral. It was used while a request was being processed, potentially reused as the cache. But what KV cache would like what LM cache would like to do is to make it a first-class citizen. So it's something the cache itself is something you can manipulate. You can move it between CPU and GPU memory or disk. You can compress it. You can pin it to a particular device. So that's one of his philosophies. The other is efficiency through optimized data movement. What that means is that each device, whether it's GPU, CPU, disk, or network, has got like a particular sweet spot, and they use that sweet spot to group pages to be sent across to a particular device, so that it's got that kind of intelligence in it to know, okay, this device is capable of certain throughput, a certain number of pages should go through it at a particular time, and they can kind of batch that up to make the best use of that. There are other philosophies to make it modular and compatible. Well, what that means is that what they've basically done is they've created an API for LMCache. Any inference engines, whether it's VLLM or SGLang, it's the same interface. So it's a fairly small and well-defined API that an inference engine can actually call into LMCache to actually make use of a KV cache. They also give explicit management controls. So you can pin cache to particular devices in memory. You can move it, compress it. You can evict it using APIs. And because of this architecture that they have, it really readily fits into Prefill-decode disaggregation, because there you potentially have two different instances, one doing the prefill and one doing the decode. And because the KV cache is a completely separate first-class citizen, you can actually share it. And what it also allows, because the KV cache here is a first-class citizen, you can share it across queries, but also across inference engines. So that if you've got a cluster of inference engines, you could have a shared KV cache, and that can be shared across the different instances. And we'll see in a second how they make use of that. So those are kind of like the overall philosophy of what drives LMCache and makes it so kind of performant and so sort of versatile. So the overall architecture of this here is kind of in the middle. That's where LMCache is, and you've got storage engines, a wide variety of supported GPUs, CPUs, Redis, and you can create kind of like new ones. And then an API, well-defined API that inference engines can use. And currently, VLLM supports it, and so does SGLang. This is kind of like the architecture of LMCache as like a thing. It's broken down quite a bit. Essentially, it's actually two processes. So it's actually the cache controller process, which is kind of like in the middle here, and then this worker process, which is this big guy here. And the cache controller is essentially the API that other kind of systems can talk to. The router, which is routing the request to the different inference engine instances, can talk to it. And the worker is really what's responsible for actually dealing with the cache. It has connectors to GPUs. It has connectors to the different backends, the storage backends that it supports. So this is kind of like the high level. And this is what makes it distributed, because it's kind of like split into two separate kind of devices, two separate processes. You can run it, on different instances in on your network. Now, obviously, this is quite high level and it's quite difficult to understand. So what I decided to do was to actually create kind of a request that was going to come in through to the system and then kind of see how it's kind of processed through it. So step one, once a request arrives, so the user sends a prompt or a query to the system, and so something tokenizes the input and the metadata. And the very first step is that your router can actually call into LMCache, and if we see it, because that's the bit right at the top here, your router. And the reason it wants to do that is that potentially the cache is already on a GPU on one of the instances, or it could be a CPU or some device. So basically, the router is asking the various LMCache instances that are available on your cluster. I've got this query. These are the tokens that it has in it. Have you got a cache that you can already use? So that it kind of identifies what's the best instance to kind of send this particular request to, so to make any cache that it already has available without having to load it from from slower storage. So as part of that, any system that it sends the query to can say to it, hey, I have got cache and I've got this many tokens. And then what the scheduler allows that to do is to say, okay, some stuff's cached, but some stuff needs to be computed. So at this point, it can actually break down, okay, this stuff needs to go to the prefill server to compute the prefill. This stuff is already in cache, so we can already use it. So this first step essentially does that kind of like breakdown between those two. So the cache that we already have and the cache that we need to now compute, because it needs to go to get the prefill done. So the next step is we know now that we've got a certain amount of data that we need the GPU. So we can pre-allocate the number of pages that are needed. Obviously, the cache ones we already have, or potentially. So this is this intelligent page mapping, which is the cache pages that we already have, we can just reuse. Any new pages that we need, we can allocate those. And then from that, we can see, okay, this is the cache that we need to load. And so this is quite intelligent, because it's actually being able to give the system the GPU memory addresses for where the cache pages should be loaded. So LMCache, because it has a GPU connector, can load cache directly into the GPU without having to, without having to go through the inference engine, because the inference engine API actually gives LMCache the buffer addresses where the data should actually be loaded into. So this is where that transfer planning is done. So this is where, so one of the optimizations LMCache does is that because the computation that's needed to be done can be done in parallel with the transfers, data transfer from the KV cache. So what it does is it loads the cache for the current layer and starts the compute of the attention. And in parallel, in async, it loads the cache for the next layer. So that by the time this compute is finished and the next layer is potentially already actually loaded, its cache is already loaded. And then the cache for the next layer and starts the attention, the compute for that, and then the next layer is loaded in parallel with that. So this layer-wise pipelining is kind of like an efficiency, making use of this the idle time the way the compute is happening on there to be able to transfer the cache for the next layer. So so one of the other steps is that any new tokens, because it may be that you've got cache for some stuff which you can start computation on, but there's other stuff that needs prefill which you can't start the computation on. So in parallel, it will also start generating the prefill for that. So it's kind of like a dynamic kind of system. What you've got, you can start on, but the stuff that you don't have, you can start the prefill on that. And finally, we've got the autoregressive decoding. So this is VLM generates a token one by one, and each new token potentially creates more KV cache. Now, because we're not transferring the KV cache like per token, this is kind of batched up into pages, and then multiple pages are kind of like as a chunk sent across to the various storage backends. And this is kind of like the efficiency of deciding what is the best amount to send to the different sort of backends. So depending on whether you're offloading to CPU or whether you're offloading to disk or over the network. And finally, you've got the tokens streamed back to the user, and then obviously you've got the performance improvement because you've improved because you've got cache hits, you've reduced the amount of compute that you need to do. So KV cache remains in the backend because it's kind of paged. You've got a better chance of being able to make use of it the next time. You've got APIs to pen it, compress it, so on and so forth, and eventually it's evicted, or you can explicitly clear it out using an API call. They have done some, because obviously some KV cache they're storing over the network, they have done some kind of like performance on whether it's easier just to recompute something or actually bring it over the network for a cache. And they've got like a certain amount of data. So if you've got more than like, I think it was 256K, it depends on your network, obviously, and kind of like the latency on that. But you can kind of decide, okay, if I only have to compute the 64K of these token, worth of these KV, I'll just use the GPU to do it. Or actually, there's enough KV cache that are in the system that I can make use of it because it's sufficiently large that it's better for me to load it rather than have it recomputed. So it's got that kind of intelligence in it. It can decide it's either cheaper to just compute it, or actually it is worth grabbing it over the network, depending if it's got if there's a certain amount of latency, because you don't want to transfer smaller amounts.
Sorry, can I ask a quick question about
So
that?
yeah, sure.
Do you have any more detail on how it makes that determination? Is there some kind of heuristic or like what factors? Yeah, any more detail? I'm just
Uh,
curious.
yeah, so it's in the paper. They did some experiments.
Mm-hmm.
So obviously it depends on the speed of your GPU, the amount of memory you've got. But
Mm-hmm.
but but obviously there was this question, okay, if you're storing the KV cache over the network, I mean the whole
Yeah.
point of the KV cache is to speed up time to first token, and the
Mm-hmm.
inter-token latency. So like and if it's not just stored just for the for the heck of it, just to, so they did some. obviously, if it's there's no hard and fast. They did put in like a 256K in the paper, but I think it's so dependent on the speed of your network, whether you're using NVLink or whether you're
Hmm.
going over PCI Express but there is like a sweet spot at some point where it is cheaper just to download it from wherever it is than to recompute it because it would just take too long to recompute
Interesting.
it. Um,
Yeah, I had that
uh,
same exact thought this entire time. I was like, with things going, because there's like, it showed like the transfer mechanisms being both like NVLink, RDMA, or TCP, which have like wildly different network bandwidth characteristics, and yeah, just generally, if you're doing like multi-node versus single node inference, like you just mentioned, like NVLink bandwidth is going to be very different than like InfiniBand bandwidth, and I wonder if they have some kind of sort of like what's it called? Like a sort of like an auto tuning process you would run at the when you start up the inference server to kind of like run some experiments with fake data and generate some heuristics that can be used at runtime during inference to make that decision. Because like you said, it's super hardware dependent. Um, yeah.
yeah. So I mean, in the paper, they said it's controlled by system parameters.
Hmm.
So basically you define some in that config like uh, but yeah, it kind of makes sense that you will want to do that. But obviously, it's even dependent on like how heavily your GPUs are going to be used and your workloads on it. It's
Hmm.
probably going to be like an admin type decision as to what
Yeah.
level they would
Hmm.
do this. Um, yeah, I mean, it was interesting. There was a talk yesterday. There's a of a about at one of the NVIDIA sort of reading groups where they were doing a Prefill-decode. Like, when should you even use that? Because
Hmm.
depending on your model size and depending on the request size, like it might be overkill, and you're actually slowing things down.
Hmm.
Um, but again, that was just really dependent on like real measurements that you took over your requests, really to see, okay, what kind of requests are we getting? But potentially, I mean, the guy was suggesting if it's in an enterprise environment, you've got documents, you've got like a certain types of queries, you could even pre-compute KV caches for all of those. Like, if it's a large PDF, rather than having to compute each time, you could have like a database of those. So um, but yeah, so slightly that was slightly off topic, but it just reminded me of that. But yeah, I mean it's a good point because the whole point of this is to improve the performance of the system, and if
Hmm.
all you're doing is generating extra overhead for no reason, um, but yeah, I mean obviously normal DRAM is a lot cheaper than GPU HBM, so
Hmm.
there's lots of potential optimizations you can do, and LMCache is flexible enough to have this kind of tiered kind of storage mechanism
Hmm.
where they've got notions of hot cached and kind of like warm and like cold cache. So you can kind of like go down the tiers and up the tiers. So yeah, it just makes the whole process a lot more complicated. But yeah, there's always for every device there's kind of like a sweet spot of what data is worth grabbing rather than recomputing.
Yeah, I think you're right. It'll ultimately probably for any serious kind of like enterprise inference system, they would probably do their own experiments on their own specific clusters and set those heuristics or configs. Anyway, that's really
Yeah,
interesting.
yeah.
Thanks.
Yeah. So what are the key optimizations that LM Cache uses? So batch data movement, so transfer chunks instead of pages, essentially trying to optimize the kind of like the maximum throughput for each particular type of device. Layer-wise pipelining to overlap KV cache loading and computation so that KV caches are ready for when the computation needs to be done rather than loading it and then doing the computation. Zero copy operations. Here, there's quite a few of these. If the data is already in the GPU in a certain page, because we use page attention, we use that same page pointer because the system treats basically memory in kind of like a virtual way, just like normal kind of like operating systems do. And you get like read-only shared kind of pages in the virtual memory, pretty much the same kind of idea. Uh, they use as much pre-async as possible. So that virtually every device now supports the async operations for storing and reading, and they make heavy usage of it as they possibly can, so that they can be doing useful work while a certain operation is being done. And implemented a storage hierarchy so that data can either be in GPU memory, CPU memory, could be on NVMe drives, back-end Redis. So you've got like a hierarchy of those, and data can be moved up and down, kind of like between that. So those are the kind of like key kind of like optimizations that LMCache uses to get the performance that it gets. So this is, I'm not going to go through each one of these, but so basically this is the API that I was talking about. So LMCache exposes this API to inference engines. Essentially, this is what allows an inference engine to query LMCache to say, has it got any cache for a certain query and how much it does, to asynchronously load a cache, wait for loading of a cache for a particular layer, store some cache which has been computed by an engine, and wait for that store to finish. So it's pretty simple set of operations. So this is what VLLM is using to actually interface into LMCache. There's a separate set of kind of management APIs, but this is essentially the inference ones, not the management APIs. Evaluation. So, these numbers obviously they're going to vary depending on your hardware and so on and so forth. But just to kind of like get like a overall overview of, so LMCache is the green one. So it's the smallest time to first token and the inter-token token latency. And then they have the naive VLLM built-in cache and a couple of commercial products. So obviously, in virtually every case, LMCache is performing a hell of a lot better than the built-in naive VLLM implementation and the commercial one. Because the commercial one's black box, they're not quite sure why. They think it's because the commercial ones are not optimized for the I/O. So because LMCache makes heavy user facing and this chunking to put the maximum amount of throughput to each device, they think that the commercial systems are not doing that, and that's why their performance is not as good as LMCache. And they even quip that commercial systems are sometimes written in C++ or Rust, and their system written in Python and still performs better. So it's a bit of a dig on C++ and Rust that you don't have to write it. Although I'm a Rust guy, so yeah, I'm not sure that's a valid point. But yeah, that was interesting. So yeah, I'm not going to go through individual numbers here, but just to get a feel, it's incredibly high performance. It's one of the highest performance systems out there for KV caching. That was like a single node, and this is a multi-node going across an instance. And again, it performs kind of like at least as well as or better than commercial systems, and obviously a lot better than the built-in VLLM alternative. A couple of I'll share these slides so if people want to go and have a look at them. But LMCache themselves, actually, I think they've started a company now to commercialize LMCache. The guys who actually built it, they're from the University of Chicago. And then there's in the VLLM, there's actually some examples of a couple of different use cases for LMCache, which they've given. And there's a YouTube video from one of the guys from the University of Chicago actually presenting LMCache on that. There's a few videos online sort of doing that. And that's kind of LMCache. It's I know this was quite a high level kind of talk. I wasn't sure what people were kind of expecting, but I don't know if anybody's got any questions.
I thought this was awesome. I have a couple questions. Do you know, because we talked a lot about KV cache being transferred across, the network, whether that be on NVLink on a single node or across nodes over some other kinds of network fabric. Do you know, you mentioned something about compression. Does this support KV cache quantization, which is kind of one method of doing that?
Uh, so I think, well, So basically, I think that this was a customer request they had, and what they've done is basically because they've got this plug-in architecture. So depending on how you implemented it, because I don't know if I go back to, uh, so you've got like this kind of storage manager, and you've got various backends. So there's no reason why you can't implement like a compression layer on it.
Hmm.
But like I'm not, well, I don't think you want to quantize it because then you would kind of lose the whole idea of KV cache because you want it to be like an identity function, uh, kind of, right? Like if you wanted to quantize the KV cache, you would have done it like much earlier on in the process in the inference engine.
Hmm.
So, and then you would have stored it that. But I mean, I think this is just like obviously these are just numbers. I don't know what the compression ratio is going to be. I can't imagine it's massive. But like obviously, if it's, I mean, potentially these are gigabytes worth of data. I mean, these are not small amounts of data. I
Yeah.
mean, obviously we can just say, oh, okay, this is just the query and the key, sorry, the key and the value we're storing. But actually, this is gigabytes and gigabytes of data. And for any, decent sized model, it could be like 10, 20, 30 gigabytes. So even if you're only getting 10, 15% compression, that's still like quite a bit.
Hmm.
The compression they're talking about, obviously, it's kind of like because it's a plug-in architecture, you could go and create your own but I think the built-in one is really just normal, lossless compression. They're not talking about quantization.
Okay. I know because I think what's it called? VLM has some kind of quantized KV cache, and just but kind of basically with any kind of quantization, you're going to have a separate scales tensor for how to scale the data back up to the dynamic range of your original precision, and so then all this internal machinery we're talking about here needs to be aware of this separate tensor, and the scales, need to be in the correct order associated with the elements for which that scale, each individual scaling factor applies. And I'm just like, it seems like the design of this like would need to have explicit handling for like the scales, basically. I wonder if they did that. I guess I could probably
Yeah,
just Google,
no,
yeah.
yeah, the API is really kind of at the token level. I mean,
Hmm.
VLLM would use this API, which is this store KV API,
Hmm.
uh, and I'm not sure if that's that's like a opaque pointer. I didn't look into the exact contents of that KV pointer.
Hmm.
uh, uh, but yeah, I mean, as I said, there's no mention of quantization in the paper itself.
Hmm.
And obviously, with quantization, because I mean, even if you're scaling down and up, I mean, that's not going to be like totally lossless potentially.
Hmm.
Like, really, you want to quantize, depending on whether you're doing the weights or you're doing the activations. Uh, yeah, I mean, I guess in this case it's activations because it'll be the
Hmm.
keys and the values.
Yeah.
Um,
Yeah, it's a performance
but it
versus
would be at the inference
accuracy
layer.
trade-off thing. Yeah.
Yeah, I that would be at the inference engine level. If that, yeah, I mean, I can't see that they would implement quantization in here because that would be like, yeah, it would not be the kind of thing that you really a cache layer would be doing. That would be
Hmm.
a decision that the inference engine system would do itself.
Would the inference engine, say like VLM itself, have some kind of basically it could use these kind of generic APIs we see here. It could start like an async load or store of the actual say FP8 data for the KV cache, and then also it would also use the same API for a different KV pointer that is actually for the like the FP32 scales for that FP8 data. And the cache layer doesn't know the difference. It doesn't care. It's just loading data, basically, moving data. And it's the inference engine that has the logic to treat these different tensors as having like distinct purposes, like the data and the scales. Is that how you're picturing it would work?
Yeah, I mean, obviously, the cache layer shouldn't know exactly what is in the cache. But
Mm-hmm.
what I mean is like the format of the data in the cache.
Mm-hmm.
It's got to have some metadata. It's got to be told, okay, this is this number of tokens that
Mm-hmm.
you're caching, and this is the kind of like the binary kind of like the byte array of the data that I want you to cache.
Mm-hmm.
as I say, I haven't looked into exact implementation of exactly what's in the KV pointer, but if I was making a cache, I would make it so that the metadata just kind of told me, okay, here's the number of tokens that you're storing. This is the query hash of some sort, and here's the actual raw bytes. But the cache shouldn't really care what was inside the raw bytes. It shouldn't manipulate it.
Hmm.
So in theory, if VLLM wanted to do that, all it would need to do would be to kind of like the byte that is sent across would have to have an encoding for the scaling and the data that was scaled. So there's no
Hmm.
reason why it wouldn't do that. But as I say, I'm not sure exactly what the KV pointer contains, but if I was doing it, that's what I would do.
Okay. Well, I'll pause in case anybody else has any questions. I keep selfishly jumping in. Anybody else with any comments or questions? Nothing. It's just me. All right, cool. Well, do I have anything else? Let me think. Oh, I think this is kind of implied throughout the presentation, but I just have sort of a noob question because I don't work on the inference side. So like a lot of this, like the diagrams and stuff, it was kind of from the perspective of like a single request and decoding stream for that single user prompt. Um, this obviously, I assume has like batching, you mentioned, to have like, be able to handle and like perform decoding for multiple requests at once. Is that right?
Uh, so all of that would really be so so the router's kind of going to be sending it to different. Oops, sorry. So give me back. So you are assuming there's going to be multiple inference engines. Now, obviously, each inference engine's potentially, I mean, the router's not going to do one at a time.
Mm-hmm.
So they don't go into that detail at that level because that depends on. What the router does have access to is being told by the cache, I've got this amount cache for this particular query. So kind of the router can decide, right, it's best to send that query to that kind of instance. But other than that, typically most inference engines would batch it, and then
Mm-hmm.
depending on how normally prefill is done in chunks because you don't want to have to wait for the whole prefill for a really long request to complete before you can do the next one.
Mm-hmm.
And typically, so to get like
Oh.
within the same batch so that requests are not kind of backed up just because there's a really long query.
Mm-hmm.
So yeah, I mean VLLM implements that. That's kind of like the chunk to prefill implementation that they
I
use.
see.
Um, so yeah, I would expect the inference engine to kind of deal with that. At the level of the KV cache itself, we're really dealing with kind of like pages of tokens
Mm-hmm.
and a page and it's the inference engine asking, hey, I need the KV cache for this kind of like these pages of tokens.
Mm-hmm. Okay. And it seems like there's probably also some kind of like sticky sessions to preserve context between multiple. This isn't really having to do with caching, but I'm just inference generally. There's probably sticky sessions to preserve the prior context of if I have like a, like a set, like a ongoing conversation, so to speak, like multiple prompts building up context. Um, we ensure that it's
Yeah.
routed to the same.
So yeah, so from reading the paper, I got the impression this was kind of the router because it queries what cache is available on the different instances.
Mm-hmm.
Uh, so potentially, in theory, like the this is how that kind of context would be kept. It would be okay if a certain kind of like because the we're dealing in pages, the whole request doesn't have to match. So
Mm-hmm.
the router can say, here I've got a query. How many like how many tokens of cache do you have? And in theory, this would be sort of like a sticky session. So the instance that had the most amount of cache should, in theory, get that request to process. So it makes as much of the use of the context it already has. Now, you have also got the pinning API, so that you can actually just pin some cache to an instance so that it doesn't get evicted. And that is another way of having that, so that if you knew, for instance, a certain system prompt, you would quite like it to go to like a certain instance. Then you can just have that KV cache for that system prompt pinned to that instance, and the router would kind of take care of itself by sending the request over there.
Hmm. Okay. Wow, this is awesome. By the way, are you able to share the slides or anything or make them public?
Yeah, sure. I'll actually paste it in the Discord channel.
Okay, cool. Yeah, I'd like to link it with the video and stuff. This is a good, I think this is a good kind of like survey resource of all the different components of like a high performance, inference engine. Even though we primarily focus on the cache layer, it kind of does a good job, I think, overviewing the whole thing. Um, awesome. Yeah, I think that's it for me on my questions. Anybody else? Last chance. Any questions?
Just one question from my side. I wanted to understand this, like async KV cache or KV transfer, uh, like how it works a bit more in detail. So I remember back when we spoke about like async TP, we went a bit more in detail on how that actually works, how you make it work with these like copy engines and so on. Are they using the same thing here, even though it's not strictly an intra-node setup? Or yeah, does that work like the same mechanisms? Does that work here when like you might also send the KV cache over, say TCP?
Okay, so I'm not aware of that particular technology that you're using, but if I just explain in a high level of what they're trying to do. So if you have to, like, if the KV cache is currently in a certain tier, let's say a GPU, and you now need to offload it to disk, say. So in each particular instance, they're trying to use any async APIs that are available. So because they will avoid trying to do any blocking operations if at all possible. So virtually every device, I think, has an async API now. So they make kind of maximum usage of that. So I don't know if that particular technology that you were referring to would be used, but if it was the best one for that particular device and had asynchronous APIs, high quality asynchronous APIs, that's what they would expect to use, because their whole philosophy is to do everything async as possible and avoid any kind of synchronous code.
All right, yeah, thanks.
Okay. Great. Well, thank you very much, guys. And yeah, it was fun learning about this as well.
Cool. Yeah, thanks for doing this. This was excellent. This was a really great presentation. So appreciate you volunteering this week. And yeah, we'll find a topic for next time. I think for anybody interested, next time I might volunteer to present some work on MXFP8 training for MOEs I've done. It's something I've tentatively been planning. So be on the lookout for that event. And yeah, everybody have a good rest of your weekend, I guess.